Yeah, hello everyone. My name is Florian Jetter. As already introduced, I'm working as a data scientist or as a data engineer at PyConDE. And I'm really happy to be here to finally be able to introduce this library, Kartothek, which we open sourced a few months ago. It is a library which essentially manages a table in object stores. And if you don't know what this is or what this is about, don't worry, we will cover this. We use extensively Apache Arrow and Dask behind the scenes. Yeah. So the content of today is essentially 4 pieces. So the first thing is why blob stores? Why object stores in a cloud environment? What are they? Why would we use them for machine learning applications, and how to get the most out of it? What this talk will be about is essentially why does data consistency matter, and why is this an issue in these blob stores, and why we need something like a library to take care of this. Why can we not resolve 2 very simple tools which are out there? Why do we need something else? Then finally, I'll introduce you to Kartothek, show you a bit how to get started, how to install it, and so on. And finally, I will talk briefly about what we have in mind for the future of this tool in the following months and years. To get started and to... Sorry. Technical issues here. Okay, somehow we need to skip this slide, but I want to talk to you a bit about, I want to introduce my company briefly, not for advertising purposes, but essentially to tell you what it is we are doing, because we are doing machine learning, and I think it matters quite a lot to talk about what kind of data we are actually dealing with here. And what you would see here is essentially a picture of a supply chain of a retailer. So what is this? Imagine a retailer is something like a supermarket. So what we do is essentially we try to forecast their demands and optimize their supply chains. So this entails essentially the store itself. So what will the store sell? What kind of products will it sell? How much does it need to order at the distribution center or at multiple distribution centers? What kind of trucks need to drive the wares to the stores? And what we do is essentially we employ machine learning to determine the demand for a store. So what is the store going to need to essentially perform optimally, to reduce waste, to optimize out of stock rates, and all of these business related KPIs. With this forecast, then we throw these forecasts into a big optimizer, which essentially tells us, okay, you need to order, 5 crates of bananas and a crate of beer. And how this works is we operate as a SaaS business. So the customer sends us their data every day. This data is something like, sales. So what did it sell? What does the store have in stock? But also more complicated things, which describe essentially the supply chain. So what we have is a highly relational data model, which is about, I think we have about 50 tables to describe this whole process. So this is rather complicated. And the customer sends us this data every single day. In terms of data size, because I think talking about data pipelines, this matters. If we look at the mid to large scale retailer, we can think about 1,000 locations, or maybe a bit less, a few hundreds. And a typical retailer supermarket would have 25,000 products in store. So essentially what the customer sends us every single day is about 25 million data points every single day, and for a history of about 6 years. So this is the kind of data we are dealing with here. We do all of this in Python. So we're using pandas and Parquet as a file format. I'll talk about this in a few minutes. And from this data, essentially what we generate in data, so the demand predictions we generate and the order proposals and all this output data essentially is about, per customer, say 1 billion rows a day. This is, if you multiply this and have different steps, this is the data we're dealing with. So that's about 500 gig if we would load everything into memory for every day. What makes this actually, so some people would think that's not real big data, and I kind of agree, but what makes it interesting, we are operating as a SaaS business, so they send us data and we need to deliver data, which we generate, and this within 5 or 6 hours. So every single step we have in our pipeline has a very restricted time window, and essentially to generate these amounts of data, we have, say, for our demand forecasts, an hour of time. So this makes essentially the issue, this is the issue we are facing here, that we somehow need to have very fast peak performances, and this is where essentially our data engineering comes in, where I'm also working in. If you look at how this roughly works in a very simplified setup, we have a payload database, and this is essentially a relational database. We use a multi-node in-memory database there, which is extremely well performing in this area. But if we look at machine learning, our machine learning algorithms do not, train on 50 different tables, but we somehow need to denormalize it. We need flat data and to work this. So these are quite complex join operations we need to do there, which is expensive, of course. And we are doing all of this in the cloud. So what we would like to do is essentially use a scheduler system like Dask distributed, or similarly something like Spark, if you are more familiar with this, to scale out. So how would this look like? We would have a few hundreds, essentially a few hundred CPUs, a few hundred workers who are all crunching numbers and generating prediction outputs. To do this, essentially every worker needs to connect to the database and load data. And this is where the issue, or one of the first issues, appears, because at least our database is not able to handle, say, 500 simultaneous connections and deliver data. More likely it's 20, 30, maybe 40 connections at a time if it's a really big database. So there's somehow a very serious bottleneck on the left-hand side if we want to load data, if we want to feed our algorithms. And the same, and this is actually even worse, if we want to write our results out again. So most databases, or some are very well performing in that regard, but are not very well optimized to handle the insertion of extremely large flat tables. So in our instance, we have a database which has a table lock. So essentially one worker at a time can insert data, which is a huge issue if you actually have 500 workers. So there are workarounds for that, but essentially it is slow, and you can increase of course, your database, which is quite expensive. And to scale out and essentially deliver the peak performance we need, this is an issue. And this is why we looked essentially at different storages, which suit the machine learning applications a little bit better. And this is essentially why we use cloud object stores. And what a cloud object store is, or a blob store for binary large objects, is essentially also kind of a database, but a very stupid one, because it essentially stores just large binary streams as a file. You can store some metadata in there, but essentially it is a cloud store which offers this very simple REST API, something like get data, put data, maybe get only a small chunk of that data, something like that. What's really great about these object stores is they are extremely well in scaling out. So it is not an issue at all to essentially read with 1,000 workers simultaneously from this object store, because this is what it is built for. And on the same time, it is really, really cheap. I extracted some numbers from the Azure blob store. I'm not sure if they are 100% accurate anymore, but this is really cheap and a very well suited storage for this kind of thing, because we can achieve a very high throughput and essentially don't need to pay a lot for this. This is why we want to store essentially the data for our machine learning algorithms, both for the input and for the output, in these kind of stores. But it is an unstructured data store, so it doesn't give you something like an SQL extract. You cannot simply read the data there. You somehow need to manage how the data comes in. And especially if you have these say 500 worker, every worker individually dumps its results. So then you have 500, maybe thousands of output files. Then you need somehow a specification or a definition on how to deal with all of these files. And this is essentially what a table format is. So it's more than just defining what kind of file I'm using. So we are using Parquet, also for performance reasons, but more importantly, if we have thousands of Parquet files in the store, we can read them and write them very efficiently, but what do we do with it? How do we deal with it? How do we extract the data? How can we write or even modify the data? And this is where essentially a table format, a table specification comes in. And this is what we came up with. So a data format, table format is actually something with a lot of, say, boring details. You need to worry about things like how does your data look like? What data types do you have? What kind of file formats are you using? But more importantly, what is your data? So you need to store some statistics, maybe some indexing of your data, so that you actually know, okay, if I have 100,000 files in there, but I want to read, say, something for location X, which files do I need to look at? And you don't want to implement this yourself every time you deal with these kind of things. And ultimately, how do you do something like this consistently, so that your data is actually right? You get the correct answers, not wrong ones, not missing data, not erroneous one. How do you do this consistently and efficiently? And this is essentially what a table format is about. We are not the only ones who defined these kind of things. There are very, say, common table formats out there, which are essentially implemented by tools like Hive, Spark, Dask. So all of these technologies also already have the opportunity to just store files, which looks like something like this. So if I store some files, I can essentially define something like a partition column. So I can essentially give my data a little bit more structure. That I can say, okay, in this file section, or everything which is prefixed by this file is written for the date X and some regions. So you can split your data and give it a little bit more structure to it. But the fundamental problem here is the way most libraries deal with extracting that data again. Because what so if you use Dask or Spark out of the box, what they do is, if I perform a query like this, so give me all the data for date 2019, October 9th for the region US, it essentially performs a list operation. So it just looks, okay, what kind of files start with this prefix, like a file system? What files are in this directory? And this has multiple issues. Most and for all, object stores do not perform very well for these kind of operations. This is not what they are built for. They are built for something like, you know very specifically which kinds of files you want to have, and then it performs excellent. But not like, okay, I have 1 million files in this store, please give me all of them. This is something they are very slow at, and this is essentially an issue if you are looking at performance. But what's even more serious, at least in my opinion, is data consistency. Because if you perform these list operations, you always get all of the files which are there, even if whether you want it or not. So what you can have are essentially anomalies in your data, something like you have multiple sets of files, the same files, duplicate data. You might have missing data. Think of a run where you have all of these 500 workers and the whole thing crashes. So what do you do then? So you have a partial calculation. How do you erase it? How do you communicate that this is actually done now? How do you communicate that this data set is in fact consistent and the way it's supposed to be? The same can happen if you essentially dump data in there which is just wrong. So if you just look at all the Parquet or CSV, org files or whatever which are there, how do you actually ensure that all of these are the same data? Yes, you could, of course, say, yeah, sure, I wrote them, so I know it. But what happens if other people or other applications write to this data? Do they have the same consistency layer? Do they check actually that the data types are proper, that the columns are there you expect, and so on and so forth? So there are a lot of things which can go wrong, especially if you run things automatically. and you don't want to verify these individual steps every time manually. And this is essentially there's a very simple answer to this, namely make it explicit. Do not just list all the files which are there, but know which files are there. Essentially, what the table format like Kartothek does is it explicitly tracks all files which belong to this dataset. This has multiple opportunities because, first of all, we know for a fact that the data which is there is what we expect. Second, we don't need to list anything. We just know it is there. So when we perform a read operation, it is extremely fast because we don't have to look it up. We know where it is and can start immediately processing the data. What helps here is also if you accumulate some statistics of your data. Like, okay, which product ID is in which file? That's essentially what an index is. Also in your database. An index is essentially a very simple thing where you just remember what kind of data is at what position. And this is something which is then also part of your table specification, that you calculate indices, can update these indices, modify them, and everything consistently. And all of a sudden, if you include something like indices, you don't only have to worry about what kind of files belong there, but also are these indices properly calculated? And is your entire run complete? Is everything consistent? So you need something like an atomic modification to ensure this. The same thing goes for the table schema. So especially in the Python world, data types are not very important. People think they are not very important. So you also want to have some strong consistency on that. You don't want to have different kind of data in these files, but one consistent view. Essentially, if you put everything like this together, you can treat these hundreds, thousands of files as if it was just a table. And this is what this table format is about. And if this is properly defined, it is also portable. So what this specification is about, not only Kartothek can read this, or not only Hive and Spark, essentially all of them can read the same thing. They understand all the same data, and this is very convenient if you want to use other technology, because sometimes other technology is better suited for your use case. So putting this everything together, this table format, this table specification is quite important. Especially if you track these files explicitly, you can think about, okay, what happens if I add or remove or replace some data? Something like, if you think in SQL terms, something like insert into or merge into statements. How do you do this? Essentially, if you look at the very trivial example where, say, how Hive or Dask would do it, you would delete maybe an old file. So I named it N, and put another file in there. But as you know, these are two operations, and for every modification, and if you have thousands of these in one calculation run, there are a lot of things which can go wrong. But what you want to have is one single atomic commit, essentially, what a database offers. And how this can be done is essentially you let your run through. You write all your files, you dump everything to store, but only in the end, if you know everything is exactly the way it's supposed to be, consistency is guaranteed, indices are updated, then you commit. And essentially, this uses a copy on write principle where you just don't overwrite anything. The entire file history is still there. You just write new files. And in the end, once you are certain that everything you want to do is ready for commit, you update your registry, you update your knowledge about what files needed to be included, and write essentially your metadata new. And this one atomic commit essentially gives you consistency, because it cannot happen that you commit data which doesn't belong there. The type stability, for instance, is something, at least, which annoys me pretty badly in Python, because, you know, I'm working with pandas. The data scientists in our company are all working with pandas, and data consistency is important. If you look at this example on the right-hand side, I defined two data frames. The one essentially with a Boolean column, true, false, and so on, and all of a sudden I have a second data frame. Think of this like 2 files I load, and the second data frame has a none value in there. And this is a peculiarity of pandas, of course. Pandas doesn't have nullable bools. That's a whole different topic. But what happens is the data is upcast to an object type, which essentially kills your performance entirely. Orders of magnitude worse. Sometimes it can even happen that certain operations on your data just don't work anymore, because for something like if you look at timestamps, if you want to do something like time zone localization, if it's not a timestamp anymore, if Pandas doesn't know it is a timestamp, your code just breaks. And this is why also boring things like data types in a dynamically typed language like Python is actually quite important. So you do not want to commit something which doesn't belong there. And having this guarantee, even if it means that your entire run will fail, is a good thing, because then you have data you can rely on. What we do there, and this is where Apache Arrow comes in, as I said, this is essentially part of a table format for table specification. We have a type system, and we didn't invent it ourselves, of course, but we use the Apache Arrow type system. And Apache Arrow, I don't have time to dive into too much details there, but essentially also an open format on how to exchange data in memory. So this is rather stable type format. And what we do is essentially we extract this type information, store it to our data sets, and whenever you try to modify something, we verify that whatever you do is actually compatible with what it's supposed to be doing. Some notes on the performance, because as I said, performance in reading these data sets is actually quite important. You don't want to spend all your time waiting for your data. You just want to have the data as fast as possible. And one thing we use is we employ indices, which, as I said before, is very simply put, just we remember which values belong to which file. We store this, and this is part of our table specification. You can build these indices on all columns. So if you know essentially that you want to access, a certain column and a certain value, you can build these indices and essentially have much more control about how your performance looks like, how your data behaves. In the end, second note on performance, essentially, we use Apache Parquet as a file format. This is also part of it, but this is not an exclusive choice. This is just what's best for our approach. And essentially what Parquet offers, this is also something which we use Apache Arrow for, to convert our data to Parquet. It is a very efficient file format and a columnar data format, which also offers something which is called a row group or column projection. So in the end, if I know I only want to read column A, and maybe only where A is, 0, then essentially the file itself can tell me, hey, you only need to read the first chunk of it. So this essentially saves me loading and submitting a lot of data over the network. Instead of loading an entire gigabyte of data, maybe I can get away with 50 kilobytes or whatever. And this is essentially why we prefer Parquet. In reality, this picture is of course not really accurate. In reality, this is extremely complex format, but this is something you as a user should never need to worry about. So these are a few things which are essentially resolved within something like a table management library, that you don't need to worry about these things. This what is called predicate pushdown, that you only select a subrange of a file. This is essentially handled automatically. Indices are evaluated. So the only thing you need to do is read your stuff and specify your query, essentially. And this is what Kartothek in a nutshell is. Managing these tables in an object store in a consistent way and offering a Python interface. The list of features is, kind of long, but in a nutshell, we can have very fast reading, fast query planning, and consistent data, and a very tight integration into the Python ecosystem. So we rely on Dask, we use Pandas, we use Arrow, Parquet. This is essentially what Kartothek does, is use all the open source tools which are available and plugs them together in a way that you can rely on your data. What it is good for and what it is probably not good for, this is, I think, also something which is worth mentioning. What we are doing here is essentially big data distributed processing on flat files. If you have something like this, these approaches with Dask and with Kartothek is probably very well suited for you. If you want to scale out on a cloud using Dask or something similar, something like Spark or whatever you have in mind, this is something you might want to consider. What's also, and this is just a machine learning reference where we had the biggest impact actually, these worm patterns, write once, read many times. So if you think about machine learning, these cross-validations where you read some data, fit your model, predict on another range of data, and then shuffle it around, read other data, fit, and so on and so forth. This is essentially where you do not want to do these expensive query operations over and over again. You just want to dump your data once flat and then read selections of your data, process it, and so on and so forth. This is where we achieved essentially an order of magnitude better performance by just using blob stores and consistent tables. What it is not good for, and this is just the thing how Parquet works and everything else, it's not good for real-time things, streaming applications, or if you have really complicated data, so you shouldn't try to store, 50 tables there, but try to normalize it. And these single-row update patterns are also not very performant. So if you consider or try to consider if something like this is suitable for you, just think about, hey, what kind of data access patterns do I have? Do I read a lot of stuff at once, or do I want to modify very tiny sections essentially in real time? Then this might be a deal breaker for you. But for machine learning processes, this was saved us. So how to get started with this whole thing? One very nice thing about Kartothek is that it doesn't rely on a very complex system setup. So if you think about very strong other technologies in that area, something like the Hadoop stack, this is actually quite complicated to set up. You need multiple services which need to interact with each other. But for Kartothek, it is essentially a very simple Python package, so you can just install it with pip and conda and get started. So if you think about, or if you think this might be something worth you just figured out, the code, which would, how this look like. In the upper section, this is essentially an example how you would append data to an existing data set. You just call a function, say where should I store it to, and where does it lie to. So in this case, it's on my local file system, but as I said, we are using it in production with the Azure Blob Store. And this computation will then fail if something goes wrong. And reading the data is also quite simple. In the below section, you can see an example where essentially we read data back from this data set and just give a query there. I want to have a date larger than the 1st of October and location 404. This case is then, you can essentially do this on a distributed cluster or locally on your machine. It doesn't matter too much, but this is how essentially you would interact with this data set. And this whole consistency stuff and index evaluation statistics is handled behind the scenes. So future for Kartothek is essentially improve the table format. We want to have this as an open table format, which is quite important, which is why we also open source this. We don't want to build the stuff in our ivory tower, but we want to build something which other people can also use, or maybe change ourselves in a way that it is compatible or exactly the same as other people. We want to use technologies like Presto, Hive, Spark, which were very well established in that area. Time traveling using snapshotting, something like, okay, what was the state yesterday? What is today? Compare these two. Schema evolution, hidden partitioning, and so on and so forth. If you look at this, and this is something really down the road, there is actually a really great project from Netflix, which is called Apache Iceberg, which essentially offers exactly these things. They are already well integrated in the community, and my goal would be that we essentially implement this for us, or try to use their library in a sense that everything we do is essentially compatible to all the other technologies. And yeah, that's it. Thanks.
Thank you, Julian, for introducing us to Kartothek. Unfortunately, we don't have any time for Q&A. If someone wants to talk more about the topic, you can directly contact Julian. Thank you, guys.